space. Vast, silent, and dark. We often picture it as a perfect vacuum, a cosmic void separating the stars. But this emptiness is a lie. In the shadows between suns lies a hidden universe, an ethereal ocean of gas, dust, plasma, and magnetic fields. It sculpts galaxies, forges stars, and even shields our planet from the wrath of the cosmos. This is the interstellar medium, and understanding it may hold the key to space travel, cosmic origins, and our survival. From stellar nurseries to magnetic shockwaves, from the local bubble to the edge of the heliosphere, join us as we dive deep into the invisible forces that bind the galaxy together. We gaze at the night sky and see stars, brilliant points of light, each separated by unfathomable distances. But what lies in between? For centuries, humanity assumed the answer was nothing. The word vacuum itself implies emptiness. Early astronomers believed space was a perfect void, a blank canvas upon which stars were painted. But in truth, the space between stars is far from empty. It is filled with matter, albeit incredibly diffuse. This vast collection of gas, dust, cosmic rays, and magnetic fields is what scientists call the interstellar medium, or ISM. And while it's nearly invisible to the naked eye, it plays a foundational role in the evolution of galaxies, including our own Milky Way. At first glance, the ISM might seem like a cosmic afterthought, just a few stray particles drifting through space, but collectively, it's immense. In some parts of the galaxy, the ISM makes up as much as 15% of the visible mass. It is composed of gas, mostly hydrogen, in atomic, molecular, and ionized forms, with traces of helium and heavier elements. Dust, microscopic grains of carbon and silicates, leftovers from ancient stars. Cosmic rays, high-energy particles zipping through the galaxy at near-light speeds. Magnetic fields, invisible but powerful, shaping the behavior of plasma and charged particles. Despite being extremely thin, far more so than the best vacuum humans can produce in a lab, the ISM spans trillions of kilometers. In total, it weighs as much as billions of suns. The interstellar medium isn't just background noise. It's the lifeblood of the galaxy. Star formation. All stars, including our sun, are born from dense clouds within the ISM stellar death. When stars die, via supernova or stellar winds, they return their material to the ISM, enriching it with heavy elements like carbon, oxygen, and iron. Planetary systems. Dust grains in the ISM eventually form planets, moons, and even organic molecules, the seeds of life. Galactic evolution. The ISM acts as a feedback loop between stars and the galaxy's structure, regulating star formation over billions of years. In essence, we are made of interstellar matter, forged in stars, scattered into the ISM, then reborn. Our own sun is currently drifting through a region of the ISM called the local interstellar cloud, a wispy structure of hydrogen and helium gas about 30 light-years across. Surrounding that is an even larger cavity known as the local bubble, believed to have been carved out by ancient supernova explosions millions of years ago. These structures don't just sit idly by. They interact with the outer boundaries of our solar system. The heliosphere, a protective bubble created by the sun's solar wind, pushes against the local interstellar cloud, shielding Earth from harmful cosmic radiation. In fact, fluctuations in the ISM may influence climate cycles, cosmic ray levels, and possibly even extinction events on Earth. Because the ISM is mostly invisible, astronomers use specialized tools. Radio telescopes detect the famous 21-centimeter emission line of neutral hydrogen. Infrared observations reveal warm dust clouds hidden behind opaque starlight. Ultraviolet and X-ray telescopes observe hot ionized gas from supernova remnants. Spectroscopy allows scientists to analyze the chemical makeup and motion of gas clouds. The data from these observations create detailed maps of the ISM's complex structure: filaments, voids, bubbles, and clouds, all moving and evolving across millions of years. The interstellar medium is not static. It is alive with motion, rippled by shock waves, carved by stellar winds, and magnetized by rotating stars. Some regions are frigid and still, only a few degrees above absolute zero. Others are hot plasma fields heated to millions of degrees by supernova explosions. These dynamic environments create pressure gradients, turbulence, and shock fronts, conditions that determine whether stars will form or if clouds will be torn apart. If galaxies are cities of stars, then the interstellar medium is the atmosphere, roads, and resources that allow life to flourish. Far from being empty space, the ISM is a cosmic ecosystem, one that connects stellar birth and death, planetary formation, and even the possibility of life. In the chapters ahead, we'll explore how the interstellar medium was discovered, how it protects Earth, how stars are born from its dust, and what dangers and opportunities it holds for future space explorers. But first, let's rewind the clock. How did we first learn that the space between stars wasn't empty? For much of human history, space was a mystery defined by absence. The night sky, strewn with stars, seemed silent and still. The idea that anything existed between those stars was almost unthinkable. But the story of how we discovered the interstellar medium, this hidden substance that binds the galaxy together, is not just a tale of telescopes and theories. It's a story of shifting worldviews, of scientific revolutions, and of seeing the invisible. Ancient civilizations had no concept of a medium in space. To them, the heavens were solid, serene, and divine. The Greeks imagined celestial spheres. In Aristotle's cosmology, the heavens were made of an unchanging fifth element, ether. This idea of space as a perfect void persisted well into the Renaissance. Even as telescopes improved, there was no direct evidence of anything between stars. Vacuum was assumed. Emptiness was law. And yet, some curious anomalies began to suggest otherwise. In the 19th century, astronomers began using spectroscopy, the technique of splitting starlight into its component colors. This revealed absorption lines, unique fingerprints that told scientists what elements were present in a star's atmosphere. But something strange happened. In 1904, German astronomer Johannes Hartmann was studying a binary star system, Delta Orionis, when he noticed an absorption line that didn't shift with the star's motion. It stayed fixed. That meant it wasn't coming from the star itself. It was coming from something in between, something cold and diffuse, floating in space. That line belonged to ionized calcium. And with that discovery, Hartmann had unknowingly recorded the first clear evidence of the interstellar medium. Still, for decades, scientists had no real map of what this medium looked like. It remained a ghost, suspected but unseen. Then came a breakthrough in the late 1940s. Physicists predicted that neutral hydrogen atoms should emit a faint radio signal at a wavelength of 21 centimeters. Detecting this signal would allow astronomers to map hydrogen, the most abundant element in the ISM, across the galaxy. In 1951, 3 separate teams, including Dutch-American astronomer Hendrik van de Hulst, confirmed the 21-centimeter line. Suddenly, the invisible became visible. Using radio telescopes, astronomers could now detect vast clouds of hydrogen gas, some stretching hundreds of light years. They saw spirals of gas tracing the arms of the Milky Way. They discovered dense clumps where stars were being born. The interstellar medium was no longer theory, it was real, and it was everywhere. As observations improved, scientists noticed more peculiar features: shock waves, expanding shells, and hot bubbles of gas. These were the fingerprints of supernovae, massive stars ending their lives in explosive death, and of stellar winds streaming off young hot stars. Each of these processes fed material back into the ISM, stirring it up like cosmic weather. The picture of the ISM evolved from a uniform fog to a dynamic, ever-changing environment. Some regions were cold and still, others were raging plasma fields. This turbulence, scientists realized, wasn't just noise, it was the mechanism that triggered new stars to form. By the late 20th century, astronomers had expanded beyond radio waves. Infrared telescopes, like IRAS and Spitzer, peered through dusty regions to reveal glowing clouds where stars were forming. Ultraviolet telescopes detected the faint shimmer of ionized gas. X-ray satellites observed million-degree bubbles of plasma left by ancient explosions. Each wavelength revealed a different facet of the ISM. What was once seen as a flat, static void became a layered, three-dimensional ecosystem. The more we looked, the more we saw: filaments, pillars, arcs, clouds, tunnels, structures of staggering scale and complexity. In the 2000s, massive ISM mapping projects like the HI-4 survey and Gaia mission began constructing the most detailed maps of the galaxy's gas and dust. They revealed that the Milky Way has a kind of hidden skeleton, a network of gas clouds, bubbles, and filaments forming the connective tissue of the galaxy. In fact, some astronomers now refer to this structure as the galactic web. It's through this web that stars are born, die, and transfer their material, creating the continuous cycle of galactic life. For decades, the ISM was seen as an obstacle, something that obscured our view of distant stars and galaxies. Today, it's recognized as a cosmic engine. Astrophysicists now believe that the interplay between stars and the interstellar medium is what determines a galaxy's structure, star formation rate, and even its long-term fate. And as we study exoplanets and search for life beyond Earth, the ISM plays yet another role, shaping planetary systems, delivering complex organic molecules, and even affecting radiation levels. Despite over a century of study, much of the interstellar medium remains uncharted. We still don't fully understand how magnetic fields influence ISM dynamics, how cosmic rays travel through this medium, how the ISM interacts with dark matter, or how changes in our local cloud might affect Earth's future. But what we do know is this: the ISM is not a backdrop. It is the stage, the orchestra, and the echo chamber of galactic evolution. And it holds secrets we've only just begun to uncover. We often think of space as the final frontier, an empty void, a vacuum stretching endlessly between the stars. But in truth, Earth is not drifting through an empty abyss. We are traveling through a vast, invisible ocean of gas, dust, and magnetic fields known as the interstellar medium, ISM. This hidden sea not only shapes the birth of stars and galaxies, it also affects Earth directly, influencing our planet's environment, space weather, and even the conditions for life itself. In this chapter, we'll explore the protective roles and potential dangers of the ISM, diving into cosmic bubbles, solar shields, and the mysterious local interstellar cloud. You'll discover how Earth's safety depends not just on our sun, but on where we are drifting through the galaxy. Earth orbits the sun, but the sun itself is on a grander voyage. It orbits the center of the Milky Way, completing one revolution every 225 million years. As it moves, the entire solar system plows through the ISM at roughly 828,000 kilometers per hour. Imagine the sun as a ship, Earth as a passenger, and the ISM as a sea filled with currents, clouds, and storms. This ever-changing environment shapes what reaches our planet and what doesn't. But unlike earthly oceans, this sea is made not of water, but of plasma, cosmic dust, energetic particles, and magnetic fields. And what lies ahead can mean the difference between stability and catastrophe. Surrounding our solar system is a giant magnetic bubble known as the heliosphere. This is the region where the solar wind, charged particles emitted by the sun, pushes back against the pressure of the ISM. Think of the heliosphere as Earth's cosmic force field. It stretches over 100 astronomical units, nearly 3 times the distance to Pluto. Its boundary, called the heliopause, marks the point where the solar wind is finally overpowered by the pressure of the ISM. Inside this bubble, we're relatively safe. The heliosphere shields us from galactic cosmic rays, high-energy particles from supernovae that can damage DNA and disrupt satellites. Without this protective layer, Earth's atmosphere would be bombarded with radiation, and life as we know it might not exist. Right now, our solar system is passing through a region of the ISM known as the Local Interstellar Cloud, LIC, a fluffy, partially ionized cloud of gas and dust about 30 light-years across. We've been in it for tens of thousands of years and will remain inside for at least several thousand more. This cloud has a density of about 0.3 atoms per cubic centimeter, and it travels at 28 kilometers per second relative to the Sun. It's warm, about 7,000 Kelvin, but still incredibly diffuse by earthly standards. Yet even at this faint density, the LIC plays a critical role. It compresses the heliosphere, changing its shape and size. It can alter the influx of cosmic rays reaching Earth. It may influence the chemical composition of the outer solar system. Some researchers have even speculated that changes in our local interstellar environment, like moving into a denser or more ionized region, could have influenced mass extinctions or climate shifts in Earth's past. While the heliosphere protects us, that protection isn't infinite. As we move through the galaxy, we may one day enter regions of the ISM where that shield fails. 1. Supernova shockwaves. If a supernova were to explode within 30 light-years of Earth, the shockwave could reach us. Even if the star is long dead, its remnants, shock fronts, and hot plasma could compress the heliosphere or even penetrate it. A supernova nearby could strip away parts of our ozone layer, exposing the surface to harmful ultraviolet radiation, increase cosmic ray flux, potentially triggering genetic mutations or cancers, cause atmospheric ionization, leading to climate disruption. Some scientists believe that a supernova might have contributed to the late Devonian extinction around 360 million years ago. Second, dense interstellar clouds. Imagine Earth entering a denser region of the ISM, say a cold molecular cloud. If the heliosphere shrinks dramatically, more galactic radiation would reach our planet. In extreme cases, such clouds could trigger geomagnetic storms, disrupt satellite networks and power grids, affect radio communication and navigation systems on Earth. Such events wouldn't be as sudden or dramatic as asteroid impacts, but their long-term effects could be just as devastating. Galactic cosmic rays, those high-energy particles traveling through the ISM, don't just pose a risk to astronauts and electronics. Some researchers suggest they may play a subtle but important role in Earth's climate system. According to the Svensmark hypothesis, cosmic rays influence cloud formation. More rays equals more clouds equals cooler Earth. Fewer rays equals less cloud cover equals warmer Earth. Although still controversial, studies have found correlations between solar activity, cosmic ray intensity, and climate variations. If we enter a denser region of the ISM and the heliosphere shrinks, cosmic ray levels would rise. Over centuries, this could shift global climate patterns. To monitor these threats and explore the ISM firsthand, we've launched some of the most daring space missions in human history. Voyager 1 and 2 are now traveling outside the heliosphere, sending back data on the true interstellar environment. IBEX, Interstellar Boundary Explorer, maps the edges of the solar system, detecting particles that leak across the heliopause. New Horizons, after its flyby of Pluto, continues to study the distant reaches of our solar neighborhood. These missions are our eyes and ears in the void, guardians watching the space between the stars. We're drifting, slowly, invisibly, through the galaxy's spiral arms. The ISM ahead of us contains hot plasma regions, cold molecular clouds, and perhaps shock fronts from ancient supernovae. Over the next 100,000 years, the solar system will continue to sail through new interstellar regions, some benign, some potentially hostile. If humanity is to become a multiplanetary species, or even launch interstellar missions, we must learn to predict and navigate these regions. The ISM is not a passive backdrop. It is an active force shaping the fate of planets. For now, Earth is cocooned inside the heliosphere, a warm, protective bubble traveling through the darkness. But the ISM is always changing, always moving, and always watching. It has the power to create stars, scatter radiation, compress magnetic fields, and deliver chemical ingredients for life. But it also has the power to strip away that life. As we peer deeper into the interstellar medium, we're not just studying the fabric of the galaxy. We're studying the conditions that made us possible, and the forces that could someday erase us. Amid the dark, cold expanses of space lies a realm of quiet alchemy. It is here, in the diffuse whispers of gas and dust, that stars are born. This is the story of the interstellar medium as a cosmic cradle, shaping suns, sculpting systems, and creating the very environments that allow life to flourish. The interstellar medium, ISM, might seem empty, but it is rich with the raw ingredients for stellar birth. Composed of hydrogen, helium, dust, and trace elements, these vast clouds span light years across. The densest regions, known as molecular clouds or giant molecular clouds, GMCs, are the true stellar nurseries. Temperature here can fall below -250 degrees Celsius. In these frigid depths, atoms bond into molecules, especially molecular hydrogen, H2, and dust grains begin clumping. Stars begin with a collapse. But what initiates this collapse? Gravitational instabilities play a role, but external forces often trigger the process. Supernova shockwaves compress the clouds. Galactic collisions or spiral arm passages pile up gas. Nearby massive stars emit intense ultraviolet radiation and stellar winds that sweep up gas. Once a region within the molecular cloud reaches a critical density, gravity overwhelms pressure. A protostar forms at the core of the collapsing clump. As the gas collapses inward, it begins to spin, forming an accretion disk around the core. Material spirals into the center, feeding the protostar. Friction within the disk heats it up, causing it to glow in infrared light. Magnetic fields channel material into jets that blast outward from the poles. Over tens or hundreds of thousands of years, the protostar gains mass. When core temperatures reach around 10 million Kelvin, nuclear fusion ignites. Hydrogen turns to helium, and a star is born. Leftover material in the accretion disk doesn't go to waste. Dust particles begin to stick together, forming planetesimals, which merge into protoplanets. Close to the star, rocky planets form. Farther out, ices dominate and gas giants take shape. This chaotic phase includes collisions, migrations, and even planetary ejections. Over millions of years, a stable planetary system emerges. Our own solar system was born this way 4.6 billion years ago. Stars rarely form in isolation. Most are born in stellar clusters, containing dozens to thousands of siblings. These clusters can be open clusters, loosely bound and short-lived, like the Pleiades. Globular clusters, tightly packed and ancient. Over time, gravitational interactions cause stars to drift apart, but some remain in binary or multiple star systems. These stellar families help astronomers study star formation chronologies and compare stellar evolution paths. Massive young stars live fast and die young. Their ultraviolet light ionizes the surrounding gas, creating H2 regions that glow brilliantly. Strong winds and eventual supernovae inject energy back into the ISM, disrupting some clouds while compressing others, triggering a new wave of star formation. Thus, the ISM becomes both cradle and recycler, a cosmic loop of birth, death, and rebirth. From a whisper of dust to the blaze of a newborn star, the interstellar medium crafts the very engines of galaxies. Each star, each planet, each spark of life owes its origin to this vast, invisible alchemy. In understanding the ISM, we come to understand the universal rhythm of creation itself. Imagine a blizzard, but instead of snowflakes, it's made of subatomic bullets. This invisible storm constantly bombards our planet from the depths of space. These are cosmic rays, high-energy particles that travel near the speed of light and crash into Earth's atmosphere by the billions every second. But where do they come from? And what role do they play in the galaxy's weather system? In this chapter, we'll journey through the mysterious world of cosmic rays and galactic weather, exploring how energetic particles, magnetic fields, and supernova shape the interstellar medium, and potentially even life on Earth. Cosmic rays are not actually rays but particles, primarily protons, about 90%, along with alpha particles, helium nuclei, electrons, and trace amounts of heavier nuclei. They travel through space at nearly the speed of light, carrying immense energy. Some originate from our sun, others from violent events like supernova explosions, and the most energetic ones may come from far beyond our galaxy, possibly even from quasars or active galactic nuclei, AGN. These particles were first discovered by Victor Hess in 1912 when he took a gold leaf electroscope into a balloon flight and measured increasing radiation levels with altitude. This discovery earned him a Nobel Prize and opened the doors to one of astrophysics' most exciting puzzles. Cosmic rays are generally classified into three types: galactic cosmic rays, GCRs. These originate outside the solar system, typically from supernova remnants within the Milky Way. They are the most abundant and extensively studied. Solar energetic particles, SEPs, produced during solar flares and coronal mass ejections, CMEs. While less energetic, they can have a significant impact on space weather. Ultra-high energy cosmic rays, UHECRS. These rare particles have energies millions of times greater than those produced in human-made accelerators like the Large Hadron Collider. Their origin remains one of astronomy's greatest mysteries. When cosmic rays enter Earth's atmosphere, they collide with air molecules, producing a cascade of secondary particles, including muons, neutrinos, and pions. These showers can be detected using ground-based observatories like the Pierre Auger Observatory in Argentina. Interestingly, cosmic rays play a role in cloud formation. Some theories suggest they increase the ionization of atmospheric particles, which can serve as nuclei for cloud condensation. If proven, this would connect galactic phenomena with Earth's climate, a concept known as the cosmic ray cloud connection. Just as Earth has weather systems driven by the sun, the galaxy has its own turbulent environment. Galactic weather involves shock waves from supernovae, which blast hot gas and accelerate cosmic rays, magnetic fields that guide and trap these particles, interstellar winds, flows of charged particles and magnetic disturbances that influence the shape and dynamics of the ISM. Together, these elements form a chaotic but structured system that transports energy and matter across vast distances. The cosmic rays act as both messengers and shapers of this galactic environment. Our solar system is cocooned in the heliosphere, a vast bubble carved out by the solar wind, a constant flow of charged particles from the sun. This protective shell extends far beyond Pluto and shields Earth from many galactic cosmic rays. However, the heliosphere is not static. It breathes and contracts based on the solar cycle. During solar maximum, increased solar wind pressure strengthens the heliosphere, reducing cosmic ray penetration. Conversely, during solar minimum, more cosmic rays reach Earth's atmosphere. The Voyager 1 and 2 spacecraft have passed beyond the heliopause, the boundary where the solar wind meets interstellar space, and are now sending back data on cosmic rays and the galactic environment. Supernovae are the ultimate engines of galactic weather. These colossal explosions inject vast amounts of energy into the ISM and create shock waves that accelerate cosmic rays to near-light speeds. When a massive star explodes, it not only produces heavy elements, but also sculpts the surrounding space. These remnants can trigger star formation in nearby clouds or carve out voids and bubbles in the interstellar medium. The Cygnus Loop and Cassiopeia A are classic examples of supernova remnants with ongoing effects on their surroundings. Magnetic fields are the invisible scaffolding of the galaxy. They influence how gas moves, how stars form, and how cosmic rays propagate. The ISM is threaded with these fields, often aligned along spiral arms of galaxies. Cosmic rays are charged, so they spiral around magnetic field lines. This causes them to follow convoluted paths, making it nearly impossible to trace them back to their source. It also means they can get trapped in regions of the galaxy, influencing the temperature and density of local gas. Instruments like the Planck satellite and LOFAR, low-frequency array, have provided new insights into these magnetic structures, revealing their importance in shaping the ISM. Could cosmic rays influence life on Earth? Some scientists think so. High-energy cosmic rays can damage DNA and increase mutation rates. Periods of heightened cosmic ray activity, perhaps triggered by nearby supernovae, might be linked to extinction events. For instance, a study published in the Proceedings of the National Academy of Sciences, PNAS, suggested that a supernova about 2.6 million years ago could have bombarded Earth with cosmic rays, potentially impacting the climate and megafauna of the time. On the flip side, cosmic rays have also been proposed as a driver of evolution by increasing genetic variation. New instruments are taking our understanding to the next level. IceCube Neutrino Observatory in Antarctica detects neutrinos, elusive particles born in cosmic ray interactions. Cherenkov Telescope Array, CTA, aims to image the high-energy sky with unprecedented resolution. SKA, Square Kilometer Array, will map magnetic fields across galaxies, revealing how they shape cosmic environments. We are also developing better computer models to simulate cosmic ray propagation, ISM dynamics, and star formation feedback loops. These models help scientists predict how galaxies evolve over billions of years. While space may seem empty, it's far from static. The galaxy is alive with motion, shock waves, particle storms, magnetic currents, and vast rivers of gas. Cosmic rays are the messengers of this dynamism, constantly traveling across light years to tell the story of stars that died long ago. Understanding this galactic weather is not just a scientific curiosity. It affects space travel, satellite design, and perhaps even the fate of life on Earth. As we build better observatories and probes, we edge closer to understanding the vast, stormy soul of the Milky Way. As astrophysicist Dr. Martin Lemoine puts it, cosmic rays are the fingerprints of the most violent processes in the universe. If you felt wonder, if you learned something new, if the silence between stars now feels a little more alive, like this video, subscribe to the channel, share this documentary with someone who's ever looked up and wondered what's out there. Drop a comment below. What part of the ISM fascinated you the most? The cosmic recycling? The voids? The idea that our solar system is surfing a galactic current? Let's discuss it. Stay curious, stay inspired. Until next time, keep looking up.